a charged particle interact with the magnetic field, there are certain rules that have to be followed. First off, the particles have to be moving, okay? If the particles are at rest, there's no chance of movement whatsoever. You can have a particle in a magnetic field, but nothing's going to happen. So that's number one. You have to be moving. The second thing is that if the magnetic field and the path of the particles are parallel with each other, that means that there will be no force. Everyone is at peace, okay? And mathematically, you'll see why this is going to work out. So if they're parallel, you got nothing. The angle influences the amount of force. Your maximum angle is going to be when the path of the particle is at a 90-degree angle to the magnetic field, okay? So those are the kinds of parameters. So here's the magic equation.
So we'll be in degree mode for this?
Huh?
We'll be in degree mode?
Oh, absolutely. Absolutely. So this is on this magnetic field equation right up here at the top. So let's talk about the significance of this. Obviously, you've got Q. If you don't have a charged particle, you don't have a force. So, which makes it difficult to detect the presence of neutrons, because neutrons don't have a charge. So you can shoot a neutron through a magnetic field and nothing's going to happen. It has mass, but it's not going to interact with the magnetic field. V is your velocity. That's why I said, if you don't have the object moving, you're not going to trigger force on it. B is the strength of the magnetic field, okay? Again, if you don't have a magnetic field, oddly enough, you don't have a force. That's why when I first put those electrons in there, or the electrodes in there, and generated the hydrogen and oxygen and all the charged particles, nothing moved, because there was not a magnetic field associated with it. And then you got the sign of the angle. Now, is your maximum force going to be at 0 degrees or at 90 degrees?
90.
90, why?
Sine of 1 is 1. Or sine of 90 is 1. That's I was trying to get to 1 and my brain makes the numbers.
Because the sign of 0 is
0.
0. So that's what it's like. If the angle between the path of the object and the magnetic field is 0, you got nothing. Okay, so what we're going to deal with is what's known as the right-hand rule. So I'm going to draw a horrible version of my hand. Okay, so just get this straight right now. So,
I'm right. I saw this on Instagram Reels a while ago.
We're off to a fantastic start.
Actually, that's a
Wait,
pretty
I'm
good
right.
vote.
I'm gonna be right.
Hey, I can
You
tell
can't
that.
roll that.
That was like orange.
No, he isn't.
Because it's
That's a masterpiece.
Why are the wrinkles?
It's like a,
actually
it's a
right.
really intricate
You know the creases on
way
the
off.
You know the creases on the finger from there?
Oh.
No, I don't know. You talk about the outside thing.
Wow.
It's just an intricate way to put somebody
hold
off.
on. Whose phone is ringing?
Why is my phone ringing? Is the question.
Why is it? Take that phone and put it up there.
Which,
It wasn't me this
Who the
time.
hell called me? Why?
That really isn't the question that annoys me right now.
it's
Okay.
weird.
So, you're going to have three things. You're going to have the thumb, and that shows either the direction of the current or the direction of the velocity vector. Your index finger is the direction of the magnetic field. And these fingers are the force, okay? So you kind of got this action going. So, here's a simple example. First off, and this is important, the right-hand rule with this only works for positively charged particles, okay? It does not work for negatively charged particles, okay? You can, but you just reverse it, okay? So the right-hand rule is for the standard definition of a current for positively charged particles. So you have three things in play: the direction of the current, or the direction of the velocity vector, the direction of the magnetic field, and then these fingers are usually what you're after. This is what's going to tell you the direction of the force. So,
Those supposed to be
Wait,
straight
are they
out?
out? Are they straight out?
like this.
Okay.
That is not what that drawing
Yeah,
said.
if it's negative, just invert
You
your
drew those-
Well, I was trying to draw it like a three-dimensional, yeah, I should have drawn it more like that.
Yeah, but we know what you mean now.
Yeah, so it's like this.
This
Okay.
seems like it's what you're looking at.
So, what we're gonna do is we're gonna combine these rules. So, stay with me here. So we're gonna have a wire with a current moving in this direction. So that's the direction of the current. Okay, don't worry about anything else. If here's the wire and it's in this direction, what's the direction of the magnetic field around the wire? So here's the question. On the top, are you gonna have X's or are you gonna have dots?
What do each mean again?
Dots.
X's mean in, dots mean out.
Dots. Current this way?
So I go this way, up on the top, I'm gonna have,
Dots.
Oh,
no.
I hate dots.
What?
What?
how about, here we go.
Well, those are bad too, but I mean,
So up at the top,
we don't like dots, but no.
we're gonna have O's.
I've been snacking on those since before they were shaped.
On the bottom, we're gonna have X's because it's going into the page, right? So we're gonna have X's down here. Okay, so now, imagine this. You have a wire carrying electric current. Around the wire, there is a magnetic field that's going around like this, okay? Got the visual. Now, I'm gonna shoot a proton parallel with the wire. And what I want to try and figure out is what's going to be the path of the proton, this is going to be important, of the proton as it's moving in this
The
direction.
wire bends.
So, you take your thumb and you point it in this direction. Now, here's the question. Is the magnetic field on the top pointing out or going in? So this is where you have to get a little bit creative. So you've got your current going this way, your finger is pointing out, so your other three fingers are pointing down. So the path of the proton is going to be directed towards the wire. So it's going to be interacting with this field. Current's going this way, so this is where you have to use the right-hand rule twice. The first rule is you figure out the direction of the field. Then you have the particle going in this direction, going this way. The magnetic field is coming out of the page. These fingers point down. Got it.
Also this.
Okay? Now, what if we shoot the proton down here?
Bend away.
Yeah.
Okay? So, the proton's going this way, right? Proton's going this way.
Inside.
The magnetic field is going into the page, like this. Your fingers point up. So,
Oh, you just do this. This hurts my hand.
so no matter which side you move it on, up or down, the proton is gonna be directed closer to the wire.
The field's going that way, it's going in.
Field goes in.
We're having fun making this.
That,
Does your index finger always have
Force
to
is
be 90
going up,
degrees
so that means the
from
force
the
Yes.
is going
Okay.
up.
so it's gonna be like this.
Okay.
So you're like this.
So then it, like, if you got one where your index
But if
finger
we
is
do
curved,
electron,
like,
we
your
use the left.
If what?
if your index finger is up, your other finger is down.
Yeah, so like, so here's where the angle becomes part of it.
They go the opposite way.
If the proton is shot in like this, parallel to it, then they would be parallel with each other. And if they're parallel with each other, if the path is parallel to the magnetic field, guess what? Nothing's gonna happen.
That's what you meant by parallel.
Yes.
Okay.
Wait, parallel to
These go
what?
through.
Parallel, like the magnetic field lines are like this. And you shoot it in parallel
So
with
we
it.
know if it's up here.
Then the angle, so if they're coming in parallel with each other, then nothing's going to happen.
So, it's a circle.
Okay, because I thought it first even parallel to the wire. Yeah.
No, parallel with the magnetic field. Yes, perpendicular to the wire,
Okay.
okay?
Perpendicular to the wire.
It wouldn't do nothing.
It goes just.
Yes, not the magnetic field.
It also
Now, what if the current was going in the opposite direction?
from the thing.
So your current's going like this,
Yeah.
right?
Yeah.
So what's gonna be up on the top of the wire? X's. We're gonna have X's on the top, I'm gonna have O's on the bottom. But now,
Charge is going same
I'm gonna shoot an electron
Oh.
in this direction.
Left hand.
No, chill out,
same direction.
chill out.
Same.
No, the current.
There's two ways that you can do this, okay? I care not. So one option is that you treat it like a proton, okay? Just treat it like a proton. Just use right-hand rule of proton. So if you use the right-hand rule for proton, it's coming in like this, the magnetic field is going into the page, your fingers are going to point down. So if it was a proton,
We have to go opposite of the current.
it would go
Down.
down. But since it's an electron, what do you think's gonna happen? It's gonna go up. Now, your other option is that you go, oh, no, that's confusing. Your other option is that you use the left-hand rule for electron. So it's the same idea, but this one gets a little bit jacked up. So the electron is going this way, the magnetic field is pointing into the page, your fingers point upward. Okay? So I don't care what you do. You can look at it in terms of protons and then flip it, or use the left-hand rule and use electrons.
That's a good show.
I like that.
On what?
Can't tell you mandated reporter thing.
Put a little eye.
All three of these.
Whoa.
Do I care? No.
Wow, he basically said if you kill yourself.
No.
That is exactly what I heard.
Do it.
You just put a wire.
That's
exactly what I heard.
just like put an eye on this one.
Yeah, I think the odds really got Yeah. Wait. Maybe I get my fingers skated through a bit sometimes. Yeah, it's cute, like a silver eye.
Please tell me we're just playing
Negative on your end.
So what are you gonna do? Go ahead.
Lesson in dot matrix.
I'm gonna paint our nails.
See, on that
It's going that way.
My finger bit.
So now we're gonna combine ideas, okay? So now we're gonna try and make a charged particle move in a circle. So let's go old school, okay? We're gonna go old school. So just pretend you're back in the simple days when it was just, you know, a string and a rubber stamp. Back now,
I guarantee you, it's something like that.
what's the direction of the centripetal force?
Inward.
Inward at a,
90-degree angle
to the velocity vector. Okay? Is there a force pushing it outward?
From a
God
certain
sakes,
point
no
of
one
view.
hesitate on that. Yes. What is the, does it want to fly off in a straight line? Because it has inertia. Okay. So here's my question. So imagine this is a positively charged particle moving around in this circle. Okay? So the question being is the direction correct for this thing to move in a circle? Right? So it's right-hand rule. It's a positively charged particle. So if I point my thumb in that direction, right? The magnetic field is going into the page, right? So which direction is the force? Well,
In,
towards the center, right? Not necessarily down, right? Because if it's here, if the particle is here, the force is going to be pointing upward. If I'm here, it's going to be pointing this direction. If I'm here, you see the pattern, okay? No matter where it is, which direction does the force point? Inward. Oh, therefore, that's going to create centripetal force. Ooh.
what?
So, one of the things that they began to figure out once they figured out there were positive and negatively charged particles, is they would shoot them into a magnetic field. And if they knew which direction they moved in the magnetic field, they could figure out if it was positively or negatively charged. So, if I shoot this positively charged particle in here and I see it going in this direction, I know that that confirms the idea that it's positively charged. Now, could a they just sucks. Okay, I can't even change that. Oh, finally it did. Okay. So, could a negatively charged particle also go in that direction and maintain a circular path?
In that field?
The only thing that's going to change is that I'm going to have it go. I'm going to try and go in the exact same direction, but it's negatively charged.
No, I don't think
Well,
so.
Stanley, you shake your head no.
I don't
Why?
think so, because the force vector would point outwards.
Beautiful. So if it's negatively charged, okay, if you want to use the left-hand rule,
'Cause
then if it's going in that direction, the magnetic field is going inward, what's it going to do? It's going to go outward. Doesn't work. So which direction would a negatively charged particle have to travel to maintain a circular path in that magnetic field?
The other.
the other way,
This way.
the other direction.
Down.
The opposite direction? Because now if it's going this way and I point the field going this way, my finger is going to point inward. So literally, this is how you figure out, hey, whoa, what's going on? We have positive and negatively charged particles. Put them in a magnetic field. See which direction that they move. So even if you don't know what the charge is, make the observation in terms of which direction that they move. Now, you all just said correctly that there was some centripetal force. Anybody remember the equation for velocity or centripetal force that involved velocity? mv squared over r, right? Okay? Now, remember when we did planetary motion way back in the
Yes.
day?
I remember getting like a low B on that test.
What created the centripetal force to keep the planets in motion?
Gravity.
And you said the gravitational force equal to the
Other weird.
centripetal force, right? Okay, remember flashbacks, right? And that was like big G,
M1, M2.
mass of the sun, mass of the earth over r squared, and that would be the mass of the earth times v squared over r, right?
Right.
What's gonna happen to the mass of the earth?
Cancel.
Cancels out, right? But here's the point of the story. What creates the centripetal force is the gravitational force, right?
Oh, now it's magnetic.
So do you see where this is going? So if you're gonna have this thing move in a circular path, what's gonna create the centripetal force?
B.
Ah, the magnetic force, right? Which is gonna be QVB. So we're always gonna assume that it's at a 90-degree angle, so we don't have to worry about the sine theta part of this. Now, conveniently, what's gonna happen to one of the velocities?
Cancel.
Out of there.
It's gonna cancel out one of those, right?
MV over R equals equivalent.
So then you can, if you cross multiply, because I hate fractions, I get MV equals QBR. So everybody says, hey, how'd you find the mass of an electron? How'd you find the mass of a proton? Okay, literally, this is what they did.
How quick does it
Is that they shot them into a known magnetic field. And they knew how fast the particles were moving around. So they knew the velocity part of the equation. They knew the charge at this point, because this doesn't work without the charge. So if it's an electron, what's the charge?
1.6.
1.6 times 10 to the negative 19. You know the strength of the magnetic field, and you would observe the radius of the particle that it's going around. Solve for mass. There you go. Now, an interesting thing happens. Compare an electron to a proton in a magnetic field. What's one obvious difference? Well, but just in terms of them being in a magnetic field moving in a circle. Beyond that.
Direction.
Huh?
Direction.
Direction. Okay? So one's going to be going in one direction, the other one's going to be going in the other. Okay? Now, this is where you have to focus on what's going to stay the same. If it's an electron or a proton, would the charge part of this be the same? Oh, done?
Yeah.
You're welcome. Would the charge part of this going to be the same?
Yes.
Yes. You can set the velocity being the same, you can set the magnetic field being the same. So this, if you let all of this over here, this be the same, Q be the R. So then you can solve then for mass. So if you know how fast it was going in, and you know the magnetic field, you can look at this. So here's the story. What do you know about the mass of an electron versus the mass of a proton? So if you look at this in terms of radius, if the velocities are the same, the charges are the same, and you put them in the same magnetic field, which one will have a larger radius, the proton or the electron?
Electron.
So you've got MV equals QBR, right?
M down, M down.
So if you shoot an electron with the same velocity and a proton with the same velocity and the same charge and the same magnetic field, what do you know about the mass of the proton? It's bigger. So what has to happen to its radius?
Also bigger.
Oh, it also has to be bigger.
Get them next time.
Contrast. So that's another thing, because now, look, if all electrons and protons, if they were the same identical mass, they would all have the same radius, everything would be the same. The only thing that you could detect is the difference in the direction. But if you look at that in terms of mass, it's like, oh, the proton has a lot more mass, therefore it's going to have a bigger radius if everything else is the same. And that's the other way that they would figure that out. So again, magnetic and electric fields, and we'll get to electric fields, this is going to be part of the story eventually too. So basically you shoot it through an electric field to have it go straight, and then you have a magnetic field that balances that out. So you would have like an electric field going in one direction, and then you would also have a magnetic field. So the electric field would make it go in one direction, and the magnetic field would try to make it go in the opposite direction. So if you could have those two balance each other out, then you could have it go straight through there. Because if you only have a magnetic field, or if you only have an electric field, it's going to get deflected. But if you can set those two fields equal to each other, then you can make them go straight through. It's like, right, this is the only way that works. And again, sucks to be a neutron because none of this works. Okay, now we're going to go old school. What's the simplest way to calculate current? What are the units for current? Amps, right? And amps are
Per second.
Q over time, right? Cool with that. Now, if you're in a circle, velocity is 2 pi r over t, correct? Okay, old school. Go back to that lab where you swung the rubber stopper around over your head.
No, I don't.
Now, older school yet, what's the relationship between period and frequency? They're inverses of each other, right? So if I substitute 1 over frequency in there, I can write that as
2 pi RF.
2 pi, and this is just kind of general knowledge, 2 pi RF, right? Now, since this is time, and this is just kind of a big broad overview, could I take this equation and solve that for time?
Yeah.
What would you get?
2 pi r over v.
2 pi r over v?
Yes.
Could I substitute that in there
If you wanted to.
if I wanted to? So I could write that as q over 2 pi r over v,
Or qv over 2 pi r.
which becomes qv over 2 pi r equals your current.
Where have I seen that before?
Okay? So, what that means is if you know the current going through the wire, and you know, for example, the charge and the velocity, you can figure out what the radius is. Or, more importantly, if you're trying to find the charge on an electron or a proton, let's say that we lose all knowledge. We lose all knowledge of science. I was like, God, how are we going to find the charge? Okay? Well, if you happen to know a current, let's say we happen to have an ammeter. Okay, hey, we got an ammeter, we can measure the current. If we know how fast a particle is moving through there and we know the radius, we can figure out the charge on the missing particle. So we can just use that equation if we need to recreate the charge on an electron or a proton. Okay, I think that's it. That's pretty much
Please
it.
don't tell me you're gonna put a magnet in geosynchronous orbit over here.
Huh?
That
Stop
wouldn't
giving
work.
ideas.
It wouldn't work.
So, you might wanna do like some, flexes before you start this assignment. I'm just saying.
I'll warm up on the, I'll warm up on the.
Hey, can I get this favor?
Cohen, field lines.
Let's kick it over.
It's inconsistent. It would be orbit.
It's like,
Such a beautiful word, the orbit. One of the best words.
I swear to God, I'm gonna throw this pen through the wall.
If you do, you might get a little bit of catharsis from that, and you have to get another one anyway. So
I'll take one for the team.
maybe you should.
You already know it's gonna be double this Friday.
Yeah, I know.
No, it's not. I don't have to take it. It is, we all get A. That's been a while. Yeah.
Oh, I just thought that yesterday.
No, that's been a whole thing.
Those are the bad ones.
What about you, Piper?
Those are
What
terrible.
about you? You don't. This isn't for a grade for you.
Yeah, but
It's because of society
These are just.
It's all society's fault.
ever since that sanitary motion, I found we have a really good distance.
That was tough.
This isn't gonna be that bad.
What do you mean? You're not reading?
Yeah, it's not gonna be that bad. We've already done all of this,
Okay,
basically.
when you get to questions or problems 8 and 9, so what you're doing is you're finding the strength of a magnetic field and knowing distance from a wire, okay? So number 8, this will make sense when you read the question. It's a big, high voltage electrical transmission line, and you're standing underneath it. And you're trying to find the value of the magnetic field. Then you want to compare the value of that magnetic field to the Earth's magnetic field. Okay, if you don't know what the Earth's magnetic field is, right offhand, it's like 5 times 10 to the -5, okay? So the value of the magnetic field of the Earth that you all are subjected to is 5 times 10 to the -5 Teslas. Okay, so right now, we're subjected to 5 times 10 to the -5 Tesla. It's a good thing. We're in the Earth's magnetic field. It's good. So what you want to do is find the strength of the magnetic field around that wire and then compare that to the Earth's magnetic field that you're subjected to all the time. On number 9, that's going to relate to if you're laying underneath an electric blanket and they give you the current and you're trying to find the strength of the magnetic field. The problem is on number 9, they don't tell you how far away to find, what distance to use to find the magnetic field strength. So this will make sense. So on number 9, use a distance of 10 centimeters, okay? It has to deal with a pregnant woman sleeping underneath an electric blanket, and you're finding the value of the magnetic field that the baby is exposed to. I'm just telling you. But no, it's a cool comparison,
Wait, so
okay?
are pregnant ladies not allowed to use electric blankets?
Well, you'll see why you can, once you get
So it's
down
gonna
with
be a
that problem,
small number.
okay? I'm just telling you, when we get down with that problem.
Just turn the electric blanket away and crank that sucker.
You're saying I should put in the
Okay, you're on your own, good luck.
like an ultra powerful magnet. Yes.
All right, Danny.
Big ass magnet.